Done. Okay, guys, I'm in the middle of writing a proposal for my research. It's a paragraph describing my research in 4 or 5 sentences, and then I want to send it to my friend so that he sends to his friend that probably is doing the related work in eBay, and through him we can start a paper together that ends up being in a project that is applicable. Please. So my sentences so far are: firms compete for a higher rank for more visibility on a recommender system platform like eBay, right? Like Amazon, like Google, through buying sponsorship to promote their product or setting prices. Reviews from consumers who purchased. Well, that's like reviews from the consumers for the product. Well, the product reviews from the consumer. Product reviews from consumers affects the ranking. Okay, products reviews from consumers that depends on their price and quality affects the firm's ranking. Wow, that's beautiful. I think we game logic too. We know how logic works, and we say, oh, okay, now that it works, let's game it. Let's game it. Firms compete for a higher rank for more visibility on a recommender system platform like eBay, Amazon, or Google through buying sponsorship to promote their products or setting prices. Products reviews from consumers that depend on their price and quality affects the firm's ranking. Products reviews from consumers that products reviews from consumers. Well, we know reviews are from the consumers, so let's remove consumer. Products reviews that depends on their price and quality affects the firm. Firm's ranking. Products reviews, volume of sale, setting prices, instead of saying products reviews that depends on their price and quality affects the firm's ranking, let's say platforms platform updates the platform updates firms ranking based on the platform updates firms ranking based on the consumer's review and the platform updates firms ranking based on the consumer's review and success in sale sales. And volume of sale. Volume of sale, consumers review, leave review based on consumers leave review based on the quality of the product and its price. We try to find the best strategy for firms, for the competing firms on the platform, and the revenue platform generates through pay-per-click service and how the revenue platform generates through pay-per-clicks and how it depends on the parameters of ranking in a game theory setting. I hope this is good. Let's read it one more time. Firms compete for a higher rank, for more visibility on a recommender system platform like eBay, Amazon, or Google, through buying sponsorship to promote their products or selling prices. Platform updates firms ranking based on the consumer's review and volume of sale. Platform updates firms ranking based on the consumer's review. Review? The platform updates firms ranking based on the consumer's review and volume of sale. Consumers leave review based on the quality of the product and its price. We try to find the best strategy for the competing firms on the platform. The revenue and review, fuck that! Revenue and review. Revenue platform generates through pay-per-click service and how it depends on the parameters of the ranking algorithm in a game theory setting. I first studied means I sent it. Alright. I first studied. Fuck. Okay, that's it. Bro. And I also sent another message. This is the shit, bro, to confirm that I really like what I sent. Alright, now let's jump quick Telegram and let's start watching some machine learning chill activities. Geoffrey Hinton on working with Ilya. Who is Ilya? Choosing problems and power of intuition. Who are these people? Geoffrey. Shift 2. Have it. Who's this guy?
Work together, or have you?
It's just these symbolic manipulations on things that are like strings of language strings. So that's one extreme view. An opposite extreme view is no. Once you get inside the head, it's all vectors. So symbols come in. You convert those symbols into big vectors, and all the stuff inside is done with big vectors. And then, if you want to produce output, you produce. It was crossed with the situation because it did not slow us down.
Yeah, it's the interviewer. Okay. This is what I like. Do.
Welcome to CS229 Machine
Oh,
Learning.
back to Andrew. Yeah, I will
Okay,
check.
happy Halloween. What I want to do today is share with you advice for applying machine learning. And you've heard me allude to this before, but I think over the last several weeks, you've learned a lot about the mechanics of how to build different learning algorithms, everything from linear regression, logistic regression, SVMs, random forests, neural networks. And what I want to do today is share with you some principles for helping you become efficient at how you apply all of these things to solve whatever application problem you might want to work on. And so a lot of today's material is actually not that mathematical. There's also some of the hardest material in this work, in this class to understand. It turns out that when you give advice on how to apply a learning algorithm, such as, don't waste lots of time collecting data unless you have confidence it's useful to actually spend all that time. It turns out when I say things like that, people, it's easy to agree. It's like, of course, you shouldn't waste time collecting lots of data unless you have some confidence it's actually good use of your time. That's like a very easy thing to agree with. But the hard thing is when you go home today and you're actually working on your class project, right? To apply the principles we talked about today, when you're actually on the ground talking to
I
your
love principles. Like, they are guidelines, rule of thumbs. They're not rules.
teammates saying, all right, do we collect more data for our class project now or not? To make the right judgment call for that, to map the concepts you learned today to when you're actually in the hot seat, making a decision. Do we go and spend another 2 days scraping data off the internet, or do we go and tune this parameters algorithm? To actually make those decisions is actually, it often takes a lot of careful thinking to make the mapping from the principles we talked about today, and then probably all of you go, yep, that makes sense. But to actually do that when you're in the hot seat making the decisions, that's something that will often take some careful thought, I guess. And I think, for a long time, parts of machine learning have been in art, right? Where we'll go to these people that have been doing it for 30 years and say, hey, my learning algorithm doesn't work. What do we do now? And then they would have some judgment, or people would ask me, and for some reason, because we've done it for a long time.
As I noticed, machine learning and research is an art. It's just not every part can be proven. No, proof, theorem, proposition. No, it's not like that. Now in my other project on the Gaussian, we are like drawing plots, but which plots to plot, not which plots, which set of parameters to choose really is just a matter of art. You need to check different things, have good intuition about the problem. Some of the plots you draw, they are not good, they are not representative of the model. You should not plot them. Go other data sets, just a lot of trial and error.
We'll say, oh yeah, get more data, or tune that parameter, or try neural network with big hidden units, and for some reason it worked. And what I hope to do today is turn that black magic, that art into much more of a science, so that you can much more systematically make these decisions yourself, rather than talk to someone that's done this for 30 years, that for some reason is able to give you the good recommendations, even if, but turn from more of a black art into more of a systematic engineering discipline. And just one note, someone I'm going to do.
Well, I think once he said like turning it into science was just he's disproved all of the things I said. But I think there is an element that we don't understand machine learning. Like there is an element of intuition there.
Do today is not the best approach for developing novel machine learning research. If your main goal is to write research papers, some of what I'll say will apply, some of what I say will not apply, but I'll come back to that later. But so most of today is focused on how to help you build stuff that works, right? To build applications that work.
Let's go principle.
So the three key ideas you see today are, first is diagnostics for debugging learning algorithms. One thing you might not know, or
by the way, I learned today that Bring ChatGPT, that we don't need to be code developers to design apps. We can just what is this? I thought it would show me a photo. Okay, show me photos. Okay. Oh, perfect. They are good actually. Alright. Now, how can do I need to know coding to build an app, or there are softwares that help me build an app? Dude, no code and low code platforms. Again, just if you have ideas. I had an idea today. I wanted to, every time these ideas come to my head, say, oh, I have to go after a lot of software developers. No, just try that. Actually, I want to try that. Mhm. That's good. Yeah, we can do that. Actually, we don't need that. Let's try. Let's try to do app, to build an app next time. You open the app and it, I don't know, tells you what you should do next time.
If you work on a class project, maybe you know this already, is that when you implement a learning algorithm for the first time, it almost never works, right? At least not the first time.
Dude, this is so important. The same when we are coding. Dude, whenever you code first time it doesn't work, it doesn't matter. It's a trial and error, right? Process.
And so,
Art.
what was it? I still remember.
I told you, it's an art. But we have some rules and principles that, like, exactly similar to these layers we had, that we have, like, oh, if it is the whole space of nonlinear functions, that will be too much. But still I can use just arctangent and, I don't know, linear mapping. I have access to a lot of functions, right? The same here. It's art, it's creative, but still there are some principles that we know work, so we are not lost.
It was the algorithm for the first time. It almost never works, right? At least not the first time. And so, what was it? I still remember. There was a weekend about a year ago where I implemented softmax regression on my laptop, and it worked the first time. And even to this day, I still remember that feeling of surprise. Like, no, there's got to be a bug. And I went in to try to find a bug, and there wasn't a bug. But it's so rare. So learning algorithm works the first time. I still remember it over a year later. And so a lot of the workflow of developing learning algorithms, it actually feels like a debugging workflow, right? And so we want to help you become systematic at that. Two key ideas here about our error analysis and ablative analysis. So how to analyze the errors of your learning algorithm, and also how to understand what's not working with the error analysis, and how to understand what's working, which is ablative analysis. And then finally, some philosophies on how to get started on a machine learning project, such as your class project. Okay? So let's start with discussing debugging learning algorithms. So what happens all the time is you have an idea for a machine learning application, you implement something, and then it won't work as well as you hoped. And the key question is, what do you do next, right? When I work on a machine learning algorithm, that's actually most of my workflow. We usually have something implemented, it's just not working that well, and your ability to decide what to do next has a huge impact on your efficiency. I think what When I was an undergrad at Carnegie Mellon University, I had a friend that would debug their code by, they write a piece of code, and then, as always, when you write a piece of code, initially always a bunch of syntax errors, right? And so their debugging strategy was to delete every single line of code that generated a syntax error, because it was a good way to get rid of syntax. So that wasn't a good strategy. So in machine learning as well, there are good and less good debugging strategies. Mm-hmm. So let's start with a motivating example. Let's say you're building an anti-spam classifier, and
that
let's
was
say
just like, what is the word? Like carelessly ignorant to the result or the code. Like, the goal we have also tells you cannot.
You've carefully chosen a small set of 100 words to use as features. So instead of using 10,000 or 50,000 words, you've chosen 100 words that you think could be most relevant to anti-spam. And let's say you start off implementing logistic regularization. I think when talk about this, is also, there's a frequentist in Bayesian school, but you can think of this as Bayesian logistic regression, where you have the maximum likelihood term on the left, and then that second term is the regularization term, right? So that's Bayesian logistic regression if you're Bayesian, or logistic regression with regularization if you're using frequentist statistics. And let's say that logistic regression with regularization, or Bayesian logistic regression, it gets 20% test error, which is unacceptably high, right? You're making 1 in 5 mistakes on your spam filter. And so what do you do next? Now, for this scenario, I want to, when you implement an algorithm like this, what many teams will do is try improving the algorithm in different ways. So what many teams will do is say, oh yeah, I remember, we like big data.
Like trying to prove the algorithm in different ways doesn't mean they try to justify the algorithm. This is always the case, right? Sometimes our data is not clean, it has noise, and even the algorithm is correct, which we never have correct, right? So some noise comes from the input training data, some noise comes from the algorithm, and at the end we have a result that is not perfectly matched, but who are we going to blame and who is guilty for the error in the output? Is it the error in the data, or is it error in the algorithm? Well, I think if you design the algorithm, you rather justify that, oh, your data is not clean. But if you have no control over data, you say, okay, I'm going to set my algorithm better, right?
More data always helps. So let's get some more data and hope that solves the problem. So some
so
teams will say,
trying to improve the algorithm in different ways means like kind of justifying your algorithm.
Let's get more
and
training
blaming other
examples.
people.
And it's actually true.
Others.
More data pretty much never hurts. It almost always helps. But the key question is how much. Or you could try using a smaller set of features. There are 100 features, probably some where.
So more data is good, yeah. Even from more should not hurt you. Smaller features, well, simplicity usually helps.
That's relevant, so let's get rid of some features. Or you could try adding a larger set of features. 100 features, that seems small, right? So let's add more features. Or you might want other designs of the features. Instead of just using features in the email body, you can use features from the email header. The email header has not just a from to subject, but also routing information about what's the set of servers of the internet that the email took to get to you. Or you could try running gradient descent for more iteration.
Books. No, that's an old book. Wanted to publish a new book.
That never hurts, right? Usually. Instead of gradient descent, let's switch to Newton's method. Or let's try a different value for lambda. Or we say, forget about Bayesian logistic regression or logistic regression regularization.
It is good to have some go-to plans once the code is not working. Try them and then check
Let's use a totally different algorithm, like an SVM or a neural network or something, right? So what happens in a lot of teams is someone will...
Also, the algorithm you develop depends on your training set and your test set, and then you go on practice, implement it on another new data set. The algorithm depends on your data set. So I don't know.
pick one of these ideas.
Well,
Kind of
the hope is that there is a connection between input and output. If we have this assumption, then yes, it makes sense to try the algorithm for a new data set. But if this assumption is wrong,
at random. It depends on, what they happen to read the night before, right, about something, or their experience on the last project. And sometimes sometimes you or project leader will say, we'll pick one of these and just say, let's try that, and then spend a few days or a few weeks trying that, and it may or may not be the best thing to do. So I think that in my team's machine learning workflow, so first, if you and a few others sit down and brainstorm a list of the things you could try, you're actually already ahead of a lot of teams, because a lot of teams will kind of just by gut feeling, right, or the most opinionated person will pick one of these things at random and do that. But if you brainstorm a list of things and then try to evaluate the different options, you're already ahead of many teams. And I think, and I think, and then unless you analyze these different options, it's hard to know which of these is actually the best options, right? So the most common diagnostic I end up using in developing learning algorithms is a bias versus variance diagnostic, right? And I think talked about bias and variance already. If a classifier is highly biased, then it tends to underfit the data. So high bias is, actually, you guys remember this, right? If you have a data set that's like this, a highly biased classifier may be much too simple, and high variance classifiers may be much too complex, and something in between, would trade off bias and variance in an appropriate way, right? So those bias and variance. And so it turns out that one of the most common diagnostics I end up using in pretty much every single machine learning project is a bias versus variance diagnostic to understand how much of your learning algorithm's problem comes from bias, and how much of it comes from variance. I've had, former PhD students, right, that learned about bias and variance when they're doing their PhD, and then sometimes even a couple of years after they graduated from Stanford and worked, on more practical problems, they actually tell me that their understanding of bias and variance has continued to deepen, right, for many years. So this is one of those concepts is if you can systematically apply it, it'll make you much more efficient. And this is really maybe the single most useful tool I've found, understanding bias and variance to debugging learning algorithms. And so what I'm going to describe is a workflow where you would run some diagnostics to figure out what is the problem, and then try to fix what the problem is. And so just to summarize this example, listing regression errors are unacceptably high, and you suspect problems either high variance or high bias. And so it turns out that there's a diagnostic that lets you look at your algorithm's performance and try to figure out if how much of the problem is variance and how much of the problem is bias. Oh, and I'm going to say test error, but if you're developing, should I really be doing this with a dev set or a development set rather than a test set, right? But so let me explain this diagnostic in greater detail. So it turns out that if you have a classifier with very high variance, then the performance on the test set, or actually, it'd be better practice to use the holdout cross validations of the development set. You see that the error that you classify has a much lower error on the training set than on the development set. But in contrast, if you have high bias, then the training error and the tester error on the dev set error will both be high. So let me illustrate this with a picture. So this is a learning curve, and what that means.
Learning curve on the way back. Well, training set size increases, we want to have error decrease, yes.
Is on the horizontal axis, you're going to vary the number of training examples, right? And when I talked about bias and variance, I had a plot where the horizontal axis was the degree of polynomial, right? Do you fit the first order, second order, third order, fourth order polynomial? In this plot, the horizontal axis is different. It's number of training examples. And so it turns out that whenever you train a learning algorithm, the more data you have, usually the better your development set error, the better your test set error, right? It's just error usually goes down when you increase the number of training examples. And let's say that you're hoping to achieve a certain level of desired performance. For business reasons, you like your spam classifier to achieve a certain level of desired performance. And sometimes desired level of performance is to do about as well as a human can. That's a common business objective depending on your application, but sometimes it can be different, right? So you have your product manager, tells you that, or if you're leading the product, you think that you need to hit a certain level of target performance in order for this to be very useful spam filter. So the other plot to add to this, which will help you analyze bias versus variance, is the plot.
What is the desired performance? We want the error to be constant, independent of the size of the training set. Why should it be? No. Actually, the green line is what makes sense. The more training set you have, less error. And we also have training error increases. How can training error increase? Okay. We are not overfitting with the training set, right? So the model, the architecture that we generate still have error for the training set too. And this increases once we increase the training set size, which makes sense, right? If we have the same number of, nuance or layers of the same architecture, then the same number of parameters, those parameters fits better with a smaller data set. Once the size of the training set is getting larger, we will have more error on the training set. That's true.
You better your test set error, right? It's just error usually goes down when you increase the number of training examples. And let's say that you're hoping to achieve a certain level of desired performance. For business reasons, you like your spam classifier to achieve a certain level of desired performance. And sometimes desired level of performance is to do about as well as a human can. That's a common business objective depending on your application, but sometimes it can be different, right? So you have your product manager, tells you that, or if you're leading the product, you think that you need to hit a certain level of target performance in order for this to be very useful spam filter. So the other plot to add to this, which will help you analyze bias versus variance, is the plot the training error. Now, one synchropy of training error is that it increases as the training set size increases. Because if you have only one example, right? Let's say you're building a spam classifier, and you have only one training example, then any algorithm, can fit one training example perfectly. And so if your training set size is very small, the training set error is usually 0, right? Because if you have 5 training examples, probably you can fit all 5 examples perfectly. And it's only if you have a bigger training set that it becomes harder for the learning algorithm to fit your training data that well, right? Or in the linear regression case, if you have one example, you can fit a straight line to the data. If you have 2 examples, you can fit any model pretty much to the data and have 0 training error. It's only if you have a very large training set that a classifier like logistic regression or linear regression may have a harder time fitting all of your training examples. So that's why training error or average training error, average over your training set, generally increases as you increase the training set size. So now, there are 2 characteristics of this plot that suggests that if you plot the learning curves, if you see this pattern, this suggests that the algorithm has a large bias problem, right? And the two properties written at the bottom, one, the weaker signal, the one that's harder to rely on, is that the development set error or the test set error is still decreasing as you increase the training set size. So the green curve is still, still looks like it's going down. And so this suggests that if you increase the training set size and extrapolate further to the right, that the curve would keep on going down. This turns out to be a weaker signal because sometimes when you look at the curve like that, it's actually quite hard to tell, to extrapolate to the right. If you double the training set size, how much further would the green curve go down? It's actually kind of hard to tell. So I find this a useful signal, but sometimes it's a bit hard to judge, exactly where the curve will go if you extrapolate to the right. The stronger signal is actually the second one. The fact that there's a huge gap between your training error and your test set error, or your training error and your depth set error would be a better thing to look at, is actually a stronger signal that this particular learning algorithm has high variance, right? Because as you increase the training set size, you find that the gap between train and test error usually closes, usually reduces, and so there's still a lot of room for making your test set error become closer to your training error. And so this, if you see a learning curve like this, is a strong sign that you have a variance problem. Okay, now let's look at what the learning curve will look like if you have a bias problem. So this is a typical learning curve for high bias, which is that's your depth set error or your development set whole cross validation set error, test error, and you're hoping to hit a level of performance like that, and your training error looks like that, right? And so one sign that you have a high bias problem is that this algorithm is not even doing that well on the training set, right? Even on the training set, you're not achieving your desired level of performance. And it's like, look, imagine, you're looking at a learning algorithm and say, like, this algorithm has seen these examples, and even for examples it's seen as not doing as well as you were hoping. Yeah. So clearly the algorithm is not fitting the data well enough. So this is a sign that you have a high bias problem, not enough features, your learning algorithm is too simple. And the other signal is that there's a very small gap between the training and the test error, right? And you can imagine when you see a plot like this, no matter how much more data you get, right? Go ahead and extrapolate to the right as far as you want. No matter how much more data you get, no matter how far you extrapolate to the right of this plot, the blue curve, the training error, is never going to come back down to hit the desired level of performance.
Why? First of all, is it possible that training error becomes more than test error? Yeah, of course it's possible, right? I mean, this is just a sample. It's not always all there. We can set our data training set and test set in a way that happens. I don't think it is impossible. Especially if we can choose our data sets. But why is he saying that it is impossible that the... Oh yeah, okay. Training error will not go down for sure. Because we already have errors for those.
And because the test set error is generally higher than your training set error, no
generally,
matter how much
generally, not all the time.
More data you have, no matter how far you extrapolate to the right, the error is never going to come down to your desired level of performance. Okay. So if you get a training error and test set error curve that looks like this, you kind of know that, while getting more training data may help, right? The green curve could come down like a little bit if you get more training data. The act of getting more training data by itself will never get you to where you want to go. Okay. So let's work through this example. So for each of the 4 bullets here, each of the first four ideas fixes either a high variance or high bias problem, right? So let's go through them and ask for the first one. Do you think it helps you fix high bias or high variance?
Try getting more training example. What did you say?
Do you think it helps you fix this problem? For each of the four bullets here, each of the first four ideas fixes either a high variance or high bias problem, right? So let's go through them and ask for the first one.
Trying getting more training example. So this is a high variance or high bias. First of all, we should do this one. I don't know. More training example leads in better bias and better variance.
Do you think it helps you fix high bias or high variance?
High variance. That's what I think.
High variance, right? Okay, cool. All right, high variance, right? Anyone want to say?
I said high variance. I said two.
Anyone want to say why? Yeah, go ahead.
Might be harder to match all of the data points and therefore I overfitting if you
Right, cool. Yes. Right. Yeah. Right. I guess if you're thinking a very high order polynomial that wiggles like this, if you have more data, it will make it. Then it won't at least oscillate so crazily even if it's a high order polynomial, right? And if you look at the high variance curve, wow, there's a lot of latency in my laptop for some reason. Huh. Right? So this is a high variance plot. And if you have a learning algorithm of high variance, you can hopefully, if you extrapolate to the right.
High variance. The more training set. High variance usually means over parameterized. Yeah, like our model is too complex. So we are using too many parameters for too little training set. So once we add to the training set, we should have better results. As M increases.
There is some hope that the green curve will keep on coming down. So getting more training data, if you have high variance, which is if you're in this situation, it looks like it could help you. It's worth trying, right? Can't guarantee it'll work, but it's worth trying.
Do we know anything about these functions?
No,
Like
there's
certain
no-
algorithms that are sampling uniformly to the distribution?
Oh, I see. Yes, sorry. This is a good point. So let's see. The curves will look like this, assuming that your training data is IID, right? Your training and depth and test sets are all drawn from the same distribution. There is learning theory that suggests that in most cases, the green curve should decay as 1 over square root of m. That's the rate at which it should decay until it reaches some base error. That's what the learning theory says. Does that make sense? And sometimes, and learning algorithms errors don't always go to 0, right? Because sometimes, sometimes the data is just ambiguous. I don't know, like because my PhD students, including on them, we do a lot of work on healthcare, and sometimes you look at an X-ray, it's just blurry, and you could try to make a diagnosis, right? Is there or actually, or Anand's working on predicting patients' mortality, right? What's the chance of someone dying in the next year or so? And sometimes you look at the patient's medical record and you just can't tell, right? What is, will they pass away in the next year or so? Or you look at an X-ray, you just can't tell, is there a tumor or not, because it's just blurry. So learning algorithms error don't always decay to zero, but the theory says that as m increases, you should decay at roughly a rate of 1 over square root of m toward that baseline error, which is called Bayes error, which is the best that you could possibly hope anything could do, given how blurry the images are, given how noisy the data is, right? All right. Oh, sorry, I gave the answer away. Okay. So try a small set of features that fixes a high variance problem, right? And one concrete example would be if you have this data set and you're fitting a 10th order polynomial and the curve oscillates all over the place, that's high variance. You could say, well, maybe I don't need a 10th order polynomial. Maybe I should use only. Oh, wow, I don't know what sorry, what's going on? That's weird. Okay, right. So maybe you say, maybe I don't need my features to be all of these things. 10th order polynomial. Maybe if this is too high variance, I'm gonna get rid of a lot of features and just use much smaller number of features, right? So that fixes high variance. And then if you use a larger set of features, fixes high bias, right? Cool, right? So that's if you're fitting a straight line to the data and it's not doing that well, you can go, gee, maybe I should add a quadratic term and just add more features, right? So that fixes bias. And adding email header features. Bias, right? Yeah, cool. Yep. Generally, I would try this to try to reduce bias, right? And so in the workflow of how you develop a learning algorithm, I would recommend that So one of the things about building learning algorithms is that for a new application problem, it's difficult to know in advance if you're going to run into high bias or high variance problem, right? It is actually very difficult.
What do you mean? Send a message. Mohammed Zaman says it's a bit better. Honestly, I don't know. How good do we want to communicate in 3 sentences?
Difficult to know in advance what's going to go wrong with your learning algorithm. And so the advice I tend to give is if you work on a new application, implement a quick and dirty learning algorithm. Have a quick and dirty implementation of something, so you can run your learning algorithm. Just start with logistic regression, right? Or start with something simple, and then run this bias variance type of analysis to see sort of what went wrong, and then use that to decide what to do next. Do you go to more complex algorithm? Do you try adding more data? The one exception to this is if you're working on a domain in which you have a lot of experience, right? So for example, I've done a lot of work on speech recognition, so because I've done that work, I kind of have a sense of how much data is needed for a new application, then I might
Also,
just build something more complicated from the get-go. Or if you're working on, say, face recognition, and because you've read a lot of research papers, you have a sense of how much data is needed, then maybe it's worth trying something because you're building on a body of knowledge. But if you're working on something, on a brand new application that you and maybe no one in the published academic literature has worked on,
causal models do not exist. They help us to understand this chaotic situation better, take one step, and then we have to adjust to the system.
Or if you don't totally
and
trust the published
our
results to be
system
representative of your
at
problem,
best.
then I would usually recommend that you build a quick and dirty implementation, look at the bias and variance of the algorithm, and then use that to better decide what to try next. Right? So I think Bayes invariance is, I think is really like the single most powerful tool I know, for analyzing the performance of learning algorithms. I do this pretty much in every single machine learning application. There's one other pattern that I see quite often, which is which adds just a second set, which is your optimization algorithm working? So let me explain this with a Mosby example, right? So it turns out that when you implement a learning algorithm, you often have a few guesses for what's wrong, and if you can systematically test if that hypothesis is right before you spend a lot of work to try to fix it, then you can be much more efficient. So let's explain that with a concrete example so you understand those words I just said. Maybe they're a little bit abstract, which is, let's say that you tune your logistic regression algorithm for a while, and let's say logistic regression gets 2% error on spam email and 2% error on non-spam, right? And it's okay to have 2% error on spam email, maybe, right? So you have to read a little bit of spam email. It's like, that's okay. But 2% error on non-spam is just not really acceptable because you're losing 1 in 50 important emails. And let's say that your teammate, right, also trains an SVM, and they find that an SVM using a linear kernel gets 10% error on spam, but 0.01% error on non-spam. Right? Maybe not great, but for purposes of illustration, let's say this is acceptable. But because it turns out logistic regression is more computationally efficient and it may be easier to update, right? You get more examples, run a few more iterations of gradient descent. And let's say you want to ship a logistic regression implementation rather than SVM implementation. So what do you do next? It turns out that one common question you have when training your learning algorithm is you often wonder, is your optimization algorithm converging, right? So, is gradient descent, is it converging? And so one thing you might do is draw a plot of the training optimization objective of J of theta, or whatever you're maximizing, or log likelihood of J of theta or whatever, versus the number of iterations. And often the plot will look like that, right? And, the curve is kind of going up, but not that fast. And if you train it twice as long, or even 10 times as long, will that help, right? And again, training the algorithm for more iterations, it pretty much never hurts. If you regularize the algorithm properly, training the algorithm longer, almost always helps, right? Pretty much never hurts. But is the right thing to do to go and burn another 48 hours of CPU or GPU cycles to just train this thing longer and hope it works better, right? Maybe not. So is there a systematic way to tell? Is there a better way to tell if you should invest a lot more time in running the optimization algorithm? Sometimes it's just hard to tell, right? So now the other question that you sometimes wonder. So a lot of this iteration of debugging learning algorithms is looking at what your learning algorithm is doing and just asking yourself, what are my guesses for what could be wrong? And maybe one of your guesses is, well, maybe you're optimizing the wrong cost function, right? So here's what I mean. What you care about is this weighted accuracy criteria, where it's sort of sum over your dev set or test set of weights on different examples of whether it gets it right, where the weights are higher for non-spam than spam, because you really want to make sure you label non-spam email correctly, right? So maybe that's the weight accuracy criteria you care about. But for logistic regression, you're maximizing this cost function, right? Log likelihood minus this regularization term. So you're optimizing J of theta when what you actually care about is A of theta. So maybe you're optimizing the wrong cost.
Okay.
function. And one way to change the cost function would be to fiddle with the parameter lambda, right? That's one way to change the definition of j of theta. Another way to change j of theta is to just totally change the cost function you're maximizing, like change it to the SVM objective, right? And then part of that also means choosing the appropriate value for C, okay? And so there's a second diagnostic which I end up using, which can help you tell is the problem your optimization algorithm, in other words, is gradient ascent not converging, or is the problem that you're just optimizing the wrong function, right? And we'll see two examples of this today. So this is the first example, okay? And so here's a diagnostic that can help you figure that out. So just to summarize this scenario, this example, this running example we're using, the SVM outperforms the regression, but you want to deploy this regression. Let's set theta SVM with the parameters learned by SVM. And instead of writing the SVM parameters as W and B, I'm just going to write the linear SVM linear kernel, using the logistic regression parameterization, right? So you have like a linear set of parameters. And let's let theta BRR be the parameters learned by logistic regression, right? So just regularize logistic regression or basic logistic regression. So you care about weighted accuracy and the SVM outperforms basic logistic regression. Okay, so this is a one-slide summary of where we are in this example. So how can you tell if the problem is your optimization algorithm, meaning that you need to run gradient descent longer to actually maximize J of theta, or is, and this is what BRR tries to maximize, right? So how do you tell? We have two possible hypotheses we want to distinguish between. One is that the learning algorithm is not actually finding the value of theta that maximizes J of theta, right? For some reason, gradient descent is not converging. So that would be a problem with the optimization algorithm. That J of theta, for the problem to be with the optimization algorithm means that if only we could have an algorithm that maximizes J of theta, we would do great. But for some reason, gradient descent isn't doing well. That's one hypothesis. The second hypothesis is that J of theta is just a wrong function to be optimizing. It's just a bad choice of cost function. That J of theta is too different from A of theta. That maximizing J of theta doesn't give you a classifier that does well on A of theta, which is what you actually care about. Okay? So this is a problem setup. Any I want to make sure people understand this. Raise your hand if this makes sense. Most people? Okay, cool. All right, almost right. Okay, good. Any questions about this problem setup? Thank you. Why not maximize A of theta directly? Because A of theta is non-differentiable, so we don't actually have, there's this indicator function, so we actually don't, it turns out maximizing A of theta explicitly is NP hard, but we just don't have great algorithms to try to do that. Okay, so it turns out there's a diagnostic you could use to distinguish between these two different problems. And here's the diagnostic, which is take the cost function that logistic regression is trying to maximize, so J, and compute that cost function on the parameters found by the SVM, and compute that cost function on the parameters found by Bayesian logistic regression, and just see which value is higher, okay? So there are two cases. Either this is greater or this is less than or equal to, right? They're just two possible cases. So what I'm going to do is go over case 1 and case 2 corresponding to this greater than or is less than or equal than, and let's see what that implies. So on the next slide, I'm going to copy over this equation, right? That's just a fact that the SVM does better than Bayesian logistic regression on our problem. So on the next I'm going to copy over this first equation, and then we're going to consider, these two cases separately. So greater than would be case 1, and less than or equal to would be case 2. Okay? So let me copy over these two equations on the next slide. Right? So that's the first equation that I just copied over here, and this is greater than is case 1. Okay? So let's see how to interpret this. In case 1, J of theta SVM is greater than J of theta BLR, right? Meaning that whatever the SVM was doing, it found a value for theta, which we've written as theta SVM. And theta SVM has a higher value on the cost function J than theta BLR. But Bayesian logistic regression was trying to maximize J of theta, right? I mean, Bayesian logistic regression is just using gradient descent to try to maximize J of theta. And so under case 1, this shows that whatever the SVM was doing, whatever your buddy implementing SVM did, they managed to find a value for theta that actually achieves a higher value of J of theta than your implementation of Bayesian logistic regression. So this means that theta BLR fails to maximize the cost function J, and the problem is with the optimization algorithm. Okay, so that's case 1. Case 2, again, I'm just copying over the first equation, right? Because this is just part of our analysis. This is part of the problem setup. And case 2 is now, the second line is now a less than or equal sign. Okay, so let's see how to interpret this. So if you look at the second equation, right, the less than or equal to sign, it looks like J did a better job than the SVM maximizing J, it looks like Bayesian logistic regression did a better job than the SVM maximizing J of theta, right? So, you tell Bayesian logistic regression to maximize J of theta, and by golly, it found the value of theta. It found a value that achieves a higher value of J of theta than whatever your buddy did using an SVM implementation. So it actually did a good job trying to find the value of theta that drives up J of theta as much as possible. But if you look at these two equations in combination, what we have is that the SVM does worse on the cost function J, but it does better on the thing you actually care about, A of theta.
Andrew.
So what these two equations in combination tell you is that having the best value, the highest value for J of theta, does not correspond to having the best possible value for A of theta.
Isn't it what he exactly
So it tells you that maximizing J of theta doesn't mean you're doing a good job on A of theta, and therefore maybe J of theta is not such a good thing to be maximizing, because maximizing it doesn't actually give you the result you ultimately care about. So under case 2, you can be convinced that J of theta is not the best function to be maximizing, because getting a high value of J of theta doesn't get you a high value for what you actually care about. And so the problem is with the objective function of the maximization problem, and maybe we should just find a different function to maximize. Okay? So, any questions about this? Yeah, go ahead.
If you wanted to change the cost function in case 2, we saw that it wasn't the correct one.
Where was this student when we had other instructors? These boys.
Yeah, let me come back to that. Yeah, it's a complicated answer. Yeah. All right, actually, let's do this first. All right, for these 4 bullets, does it fix the optimization algorithm or does it fix the optimization objective?
Actually,
First one, does it fix the optimization algorithm or does it fix the optimization objective? Cool. Second one? Oh, I don't know what's wrong with this thing. It's so strange. Okay, right. Does it fix the optimization algorithm or fix the optimization objective? Optimization algorithm, right? So Newton's method still looks at the same cost function J of theta, but in some cases it just optimizes it much more efficiently. This is a funny one. Usually you fiddle with lambda trade off bias and variance things, right? But this is one way to change the optimization objective. Although usually you change lambda to adjust bias and variance rather than this, right? And then trying to use an SVM, right, would be one way to totally change the optimization objective. So to answer the question just now, sometimes we find you have the wrong optimization objective. Is that there isn't always an obvious thing to do, right? Sometimes you have to brainstorm a few ideas. There isn't always one obvious thing to try, but at least it tells you that category of things of trying out different optimization objectives is worth your while, right? All right. So. Let's go through a more complex example. They'll incorporate some of these. Wow, I don't know what's wrong. It's probably my laptop. I wonder if it's so strange. Let me see what I can do. All right. Well. All right, let's go for a more complex example that will illustrate some of these concepts that we've been going through, and just let you see another example of these things. And I find that one thing I've learned as a teacher, one of the ways for you to become good at this, right, is to go, work in a good AI group for 5 years, right? Because when you work in a good AI group for several years, then you have seen, 10 projects, and that lets you gain that experience. But it turns out that it takes, I don't know, depending on what AI group you work on, it takes, if you work on a different project every year, then in 5 years, I guess you're working on 5 projects or something. I actually don't know, or maybe 10 projects or something. But one of the reasons that in the way I try to explain these to you, I'm trying to go give specific scenarios with you, is so that, my PhD students and I, we spent like many years working on Stanford Autonomous Helicopter, but I'm trying to distill the key lessons down for you so that you don't need to work on a project for 3 years to gain this experience, but to give you some approximation to this knowledge in maybe 20 minutes, right? And the 20 minutes won't give you the depth of the 3 years of experience, but at least try to summarize the key lessons so that you can learn from experience that others took years to develop. All right, so this helicopter actually sits in my office. But
so
if you go to my office
right?
and grab this helicopter,
let's make it first.
and we ask you to write a piece of code to make this fly by itself. Use the learning algorithm to make this fly by itself.
But I want to keep
How do you go about doing so? So it turns out a good way to make a helicopter fly by itself is to use is to do the following. Step 1 is build a computer simulator for a helicopter.
Then I want to go
that's
out
actually a
for
simulator, right? Like a video game simulator of a helicopter. The advantage of using, say a video game simulator of a helicopter is you could try a lot of things, crash a lot in simulation, which is cheap, whereas crashing a helicopter in real life is slightly dangerous and also more expensive.
They are talking about helicopter.
But so step 1, build a simulator of a helicopter. Step 2, choose a cost function. And for today, I'm just using a relatively simple cost function, which is squared error. So you want the helicopter to fly the position X desired, and your helicopter is that, wanders off to some other place X. So let's use a squared error to penalize it, right? When we talk about reinforcement learning toward the end of this quarter, we'll actually go through the same example again, but using the reinforcement learning terminology, understand this at even slightly deeper level. And we'll go over this exact same example
really
reinforcement learning, but we'll just go over a slightly simplified, very slightly simplified version.
For this
today.
one, look at this. I gave it this space here.
Run a reinforcement learning algorithm.
Look at the tip. So
and what a reinforcement learning algorithm does is it tries to minimize that cost function j of theta. And so
you can see that.
And so you learn some set of parameters, theta subscript RL, for controlling the helicopter. Right? And we're talking about reinforcement learning. You see all this redone with proper reinforcement learning notation. J is a reward function, theta R is a control policy, and so on. But don't worry about that for now. So let's say you do this, and the resulting controller, right, the way you fly the helicopter, it gives much worse performance than your human pilot. So the helicopter wobbles all over the place and doesn't quite stay where you were hoping it will. So what do you do next, right? well, here are some options corresponding to the 3 steps above. You could work on improving your simulator. It turns out, even today, you know, we've had helicopters for, what, I don't know.
I want something that, like,
I think we started having a lot of commercial helicopters around 1950s. We've had helicopters for many decades now. But
like,
airflow around the helicopter is very
for a longer
complicated.
time.
And even today, there are actually some details of how air flows around the helicopter that the aerodynamics textbook, you know, that even aeroastro people, right, the experts in aeroastro cannot fully explain. So helicopters are incredibly complicated.
By the way, number one is
there's almost
shorter.
unlimited headroom for building better, more accurate simulators on helicopter. So maybe you want to do that. Or maybe you think the cost function is messed up. You know, maybe a squared error isn't the best metric, right? And it turns out, you know, the way the helicopter has a tail rotor that blows wind to one side, right? So I guess because the main rotor spins in one direction, if it only had a main rotor, then the body would spin in the opposite direction, kind of equal and opposite reaction, but then torque, right? So the main rotor spins in one direction. If it only had a main rotor, the rotor on top, and it just spun that, then the body of the helicopter spin the opposite direction. So that's why you need a tail rotor to blow air down off to one side, to not make it spin the opposite direction. But because of that, it turns out a helicopter staying in place is actually tilted slightly to a side because the tail rotor blows air in one direction, so it's pushing you off to one side. So you have to tilt your helicopter in the opposite direction. So the main rotor blows air to one side, the tail rotor blows air to the other side, so you actually stay in place, right? So helicopter is actually asymmetric. Left and right is not the same. So because of this complication, maybe squared error isn't the best error because, you know, your orientation, your optimal orientation is actually not zero, right? So maybe you should modify the cost function. Or maybe you want to modify the reinforcement learning algorithm because you secretly suspect that your algorithm is not doing a great job minimizing that cost function. Correct? That is not actually finding the value of theta that absolutely minimizes j of theta. So it turns out that each one of these topics can easily be a PhD thesis, right? You could definitely work for 6 years on any one of these topics. And the problem is, you know, so I actually know someone that wrote a PhD thesis on, right, improving helicopter simulator, right? But the problem is maybe a helicopter simulator is good enough. You can spend 6 years improving your helicopter simulator, but will that actually get you the result? And you can write a PhD thesis and get a PhD doing that maybe. But if your goal is not just to write a PhD thesis, it's actually make your helicopter fly better. It's actually not totally clear, right? If that's the key thing for you to spend time on. So what I'd like to do is describe to you a set of diagnostics that allows you to use this sort of logical step-by-step reasoning to debug which of these 3 things is what you should actually be spending time on. Right? So is it possible for us to come up with a debugging process to logically reason so as to select one of these things to work on and have conviction and be relatively confident that this is a useful thing to work on?
So I did this.
Right? So here's how we're going to do it. So just to summarize the scenario, right? The controller given by theta RL performs poorly, right? So this is how I would reason through a learning algorithm, right? So suppose all of these things were true. Suppose that, again, corresponding to the 3 steps in the previous slide, suppose the helicopter simulator was accurate, and suppose you know, the learning algorithm correctly minimizes the cost function, and suppose j of theta is a good cost function, right? If all of these things were true, then the learned parameters should fly well on the actual helicopter.
These are not big enough wings, so
but it doesn't fly well on the helicopter, so one of these 3 things is false, and our job is to figure out is to identify at least one of these 3 statements, 1, 2, or 3, that is false, because that lets you sink your teeth into something to work on. Right? And I think
Well, I want it
to make an
live.
analogy
I don't
to more
wanna
conventional software debugging, if
like
a big
fast.
complicated program and for some reason your program crashes, like a core dumps or whatever, if you can isolate this big complicated program into one component that crashes, then you can focus your attention on that component that you know
It looks
crashes for
like,
some reason and try to find the
what
bug
is it
there.
called? Mill?
And so instead of trying to look over a huge code base, if you could do binary search or try to isolate the problem in a smaller part of your code base, then you could focus your debugging efforts on that part of your code base, try to figure out why it crashes, and then fix that
Yeah.
first. And after you fix that, it might still crash, then there might be a second problem to work on, but at least you know that trying to fix the first bug seems like a worthwhile thing to do, right? So what we're going to do is
Isn't it?
come up with a
Okay.
really great design. Come up with a
I
set of
don't believe in
diagnostics
this one
to
at all.
isolate the problem to one of these three components. Okay.
Not
so
bad.
the first step is let's look at how well the algorithm flies in simulation. Right. So what I said just now was you ran the algorithm and it resulted in
terrible.
a set of parameters that doesn't do well on your actual helicopter. So the first thing I would do is just check how well does this thing even do in simulation, right? And
From this side, it
there are two
looks like
possible
Faro.
cases. If it flies
Faro?
well in simulation but doesn't
Whatever.
do well in real life, then
shit
it
doesn't
means
work.
something's wrong with the
Yeah,
simulator.
he is Faro.
Right? It means it's actually worth working on the simulator, because if it's already working well in the simulator,
Okay, let me
I
do
mean,
it like this.
what
Change
else could you expect the reinforcement learning algorithm to do, right? You told the reinforcement learning algorithm to go and fly well in the simulator because it's just trained in simulation. It's already doing well in the simulator, so there's not much to improve on there, right? At least it's hard to improve on that. But if you found a learning algorithm, if your learning algorithm does well in the simulator but not in real
So it's
life, then
still
this
not
means that
pointy,
the simulator
but
isn't matching real
you
life
have a
well.
wider
And so
wing.
that's strong evidence, there's strong grounds for you to spend some time to
It
improve
is more
your
pointy, but
simulator.
it's not
Yeah.
super pointy. Let's see how this one goes.
Badly in the simulator, but well.
Oh yeah.
went
Is
up.
it just repeat for the camera? Is it ever the case that it flies badly in simulator but well in
Yeah.
real life? I wish that
Not
happened.
an airplane, it's the
No,
space.
actually, very rarely. I think if that happens, I would still work on improving the simulator.
There was one good
So
way to
there's
throw
actually
that
one
is
scenario where
like
that
the
happens.
other
It turns out
direction.
that
Actually, that's really good.
when we train this helicopter in the simulator, or really any robot in the simulator, we often add a lot of noise to the simulator because one of the lessons we've learned is that if your simulator
You
is
know
noisy,
why?
because simulators are always
Because-
wrong, right? Any digital simulator.
Gravity is designed to once we make our airplane like this, the standard weight, the standard direction, wings up. The gravity is designed to throw it down, right? So once you throw it like this, the airplane used to go down. Now when you throw it upside down, it tries to go up. So that's why it works. It thinks that the Earth is in the sky. Look at this. Well, I threw it bad, but another time. Okay. Fuck gravity.
Simulation is only an approximation of the real world. So we tend to add a lot of noise to all of our simulators
Let's go
because
do some
we think
content,
that
guys.
the learning algorithm is
I thought this session would be interesting, but he made it boring with all the talk about elephants, helicopters. Okay, I have to throw them. Ugh. I had 4 of them. What happened? There's just 3 of them. There is them here. Put them here. we have 3 actually. One round, honestly, one round. We are done. Ah, no. That shit was mine. Shit was glorious. Woohoo! Woohoo! I fucked just the moment I zeros. Star Surfer. Brother, I believe in you. Uh-oh. This side is no good. I can't believe. Woo-hoo-hoo. That's my gun, that's my gun. Let's go here. Guys are coming. Okay. Let's go, brothers. Woo! Where is it? Oh fuck. Why did I? Ooh. Let's go! We got the knife! Who got knife? Ooh, dude, our group was... Okay, now we are playing. One round. Shit, I didn't eat. Dude, I killed. What's happening? Oh. Who killed me? Star Surfer, motherfucker. You piece of shit. That was... Bitch. Let's go this way. Oh my god, I didn't expect that somebody come downstairs. Where are they? They don't move. Fuck you! Oh. Where? From... Dude, I'm long term on this shit. Fuck you. Shit is going crazy. Ah, fuck, I killed it. Did I kill it? Ah, fuck you, bitches. Fuck you. Then I'm happy. Okay, our guys are there. Fuck, they're so... Haha, fuck it. Fuck it. Motherfucker wants to knife me. Oh shoot, where are you? Let's go this way. Ah, fuck! Oh, fuck, where is it? Which is, they don't go upstairs. You should not let them go there. Oh, motherfucker! They're all here. Let's go fucking all of them. How does he do that? Oh fuck. How? Okay, guys, stay together. Oh, some fucking asshole. Dude, can you go to my gun? Ah, fuck. They were fucking better. Okay. Alright, guys. Let's say goodbye. I'm hungry. I didn't have lunch.